Bruce Resnick from University of Illinois in 1980 roughly joined our collaboration. And he was very excited. Later on, Bruce Resnick got Erdos #1. He beat me. He wrote a paper with Erdos much later. So he got to be Erdos #1. If you go, I went to machinekind the other day to find out my Erdos number, and I found out that indeed it's Erdos #2. But the proof was not a very good proof. It's thanks to Bruce Resnick. So ironically now, because machinekind mass reviews only started in 1940, and this paper is not listed there. So the database does not have it. So ironically, and now my Erdos #2 is not a good one. It's via Bruce Resnick. It's here. So everybody, almost everybody, unless you have no papers or unless you are antisocial and only write papers by yourself, you have a finite Erdos number. Here is a review of a few Erdos numbers. Of course, by definition, the Erdos number of Erdos is 0, that of Bruce Resnick is 1, I already mentioned, that of Zeilberger is 2, and the other invited speakers in this conference have all Erdos number 3. So they are much more removed than Erdos, and this may explain why they did not show up to my beautiful talk. Shame on you, Dave, Mitria, and Paul Erdos loved to solve problems, but he only loved to solve problems that have some chance of being solved. Some problems he did not touch. He had a good intuition. He knew they were completely hopeless. And one problem he didn't even want to consider was the 3x+1 problem, right? Lothar Collatz. And this here he is. So I'm sure most of you, or maybe all of you, must have heard of this, one of the most famous open problems. This is my favorite problem as far as easy to state. It's even easier to state than Kohlbach's conjecture and the twin prime conjectures. And mathematics is full of problems that you can explain to a 5-year-old, yet nobody has any clue how to prove it. So let me just remind you, if you take any integer, positive integer, and if it's even, you divide by 2. If it is odd, you multiply by 3 and add 1. And you keep doing it. Sooner or later, you get to 1. This is a conjecture. So, for every integer x bigger than 0, there exists a k such that if you apply C, the Collatz mapping, k times, you get to 1. Nobody has any clue how to prove it. And Erdos claimed, and was sure, that we are not yet ready to tackle such a problem. Humankind is not yet ready, and since Erdos was smart, he did not even start to think about wasting his time. But to prove it for specific cases, of course, it's easy. Here are a few specific orbits. 11, 17, for example. Sometimes you get it sooner, sometimes you get it later. And for 27, you have to be patient. We take 77 steps, but eventually we get to 1. And here is a 3. So here is the statement again. For every positive integer n, there exists a positive integer k, such that the Collatz mapping applied k times, applied to n, equals 1. True or false are meaningless. Traditionally, people believed that every statement that you can write down is either true or false, not one or the other. But thanks to Kurt Gödel, there is another option. It could be meaningless. Except Gödel did not call it meaningless. He used a more polite word. He said undecidable. No one knows. But it is true for all n less than or equal to 2 to the power 60. Has been checked by computer. But this is only a tiny fraction of all integers. So it's not a rigorous proof. The traditional dichotomy was true and false. But in my philosophy, whenever you talk about infinite sets, it's a dichotomy. True or false, or more often than not, meaningless, or not even wrong. Most statements are not even wrong, because they're complete nonsense. Why are they complete nonsense? Because they invoke the very questionable concept of infinity. Another person who doubted that everything can be solved is Alan Turing. He gave a more concrete formulation or reformulation of undecidability. So, you all know about Turing machines, or many of you know. And Turing famously proved that the so-called halting problem is undecidable. But if you look at it, it's not at all surprising that it is undecidable. Because the question is already meaningless to begin with. You have a Turing machine. This does a walk on an infinite graph, on all the possible states. There are infinitely many states. There is some rule from going from one vertex in the infinite graph to another vertex in the infinite graph. A clear-cut rule that if you have one vertex, the state, in the tape and the state, you get to another one. And the question is, can you decide that eventually you go to the halting, so-called halting state? So you have a certain set of vertices that you want to see. It's analogous to the Collatz problem. The Collatz problem asks, if you start at any given integer, if you go using the rule capital C, sooner or later you get to 1. This is a meaningless, a priori meaningless question. Because you don't have a bound. Can you do it in 10,000 steps? It's a meaningful question. Can you do it in 1 zillion, billion, Google, plex ways? It's a meaningful question. Does there exist an integer k such that either the Turing machine has after k steps or the Collatz problem has? Completely meaningless. The law of the excluded middle. Here's an example of a misuse of the law of the excluded middle. It's one of my favorite examples. Here's the theorem. There exist alpha and beta irrational numbers such that alpha to the power beta is rational. Can you find 2 irrational numbers such that alpha and beta, and alpha to the power beta, is irrational? Here's a proof, in quotation mark, an existence proof. Consider square root of 2 to the power square root of 2. Consider this number. Case 1, the square root of 2 to the power square root of 2 is a rational number. You are done. We know since the Greek times, the big scandal, square root of 2 is a rational number, the square root of 2 is rational. So if square root of 2 to the power square root of 2 is a rational number, we are done. Take alpha to be square root of 2 and take beta to be square root of 2. And case 2 is the square root of 2 to the power of 2 is irrational. Then you take alpha to be square root of 2 to the power square root of 2 and beta to be square root of 2. And then square root of 2 to the power square root of 2, quantity to the power square root of 2 is square root of 2 to the power of 2 equals 2, which is irrational. So one way or the other, there exist alpha and beta. Now a traditional, classical mathematician would have no concern, no doubts about the validity of the proof. But from my fanatistic philosophy, this proof is completely flawed. Because the dichotomy, true or false,